Hi everyone, this is the last in our preliminary review of information that you need for the course. So we're going to have a good look at set notation, specifically Venn diagrams, and then some other probability stuff. So, in a Venn diagram, this bounding box here represents the universe. We have a set A here, which would be 2, 3, 5, and 7, a set B here, which is 1, 3, 5, 7, and 9, four numbers that are outside of the sets A and B, 4, 6, 8, and 10, which gives us a universe of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, A and B. Set U, the universe, has 10 elements, set A has 4 elements, set B has 5 elements. Another way of saying that is the number of elements in the universe is 10, the number of elements in A is 4, the number of elements in B is 5. The member of symbol, this says that 9 is a member of B because we can see it's in the B circle, and 9 is not a member of A because it exists outside of the A circle. 3 and 9 are a subset of B. 3 and 9 are both in B, and that can be written like this. That's the subset symbol there. Each of the 4 zones in a Venn diagram can be named. This area here, A only, could be called A intersect not B because it's the parts that are in A that are not in B. This part here is the intersection of A and B, the parts that's common to both A and B. And this is the part of B that's not in A. And outside here would be everything that's not in the union of A and B, union being the combination of A and B, and not in it. That's what this little apostrophe or prime at the end is. Now in this case, A and not B, what's in A but not in B is 2. And the number of elements, no, that's not right. The number of elements in the intersection of A and B is actually 3. Set C is an empty set. We haven't defined set C, there's nothing in it. If we had an infinite set, if this was describing, I don't know, integers, we could write it with dot, dot, dot. And in this case, this infinite set here are the integer numbers starting at 1. And that's a member of the integer set. So, here's some notation. A intersection B is 3, 5, and 7. The intersection of A and B is 3, 5, and 7, this region. A union B is 2, 3, 5, 7, 1, 9. The union is all of the numbers in A and B. The union of A and B is 2, 3, 5, 7, 1, 9. The value is not in A prime, or A with a line over the top of it, is everything not in A. That'd be 1, 9, 4, 6, 8, and 10. And we call this the complement of A, everything that's not in A. 2 sets are mutually exclusive if they don't share any elements. So if there was nothing in the intersection, we would say that A and B are mutually exclusive. A and B in this case are not mutually exclusive because they have values in the intersection. And that's the end of our Venn diagram review. Now for probability. If this was a number line, in probability we describe how likely something is to happen by values between 0 and 1. We use the words impossible if they can't happen, 1 if they're certain to happen, unlikely if they're not likely to happen, likely if they are likely to happen, and 0.5 if they've got an even chance of occurring. We have 2 different types of probability that we're going to examine, or we have examined. Theoretical probability, which is what may happen, and experimental or empirical probability, looking at what has happened and using that to predict what's going to happen in the future. So with theoretical probability, we can find the probability of a successful outcome by taking the number of successful outcomes that exist and divide them by the total number of items in our sample space. We tend to define our sample space in 3 different ways. If it's only one thing that's happening, like a coin toss, we list it in a sample space, in this case heads and tails, and then we can find the probability of it. So in this case, the probability of one head given this sample space, there's only one head in here, there's 2 different options, of a half. Now something to note is that the things that we list in here have to be equally likely. If we have two things happening, in this case we've got 2 coins tossed, that might be the first coin, that might be the second coin. We have a sample space here, and we can then rewrite that in a list if we want to. The things that are possible if 2 coins are tossed is head, head, heads, tails, tails, heads, tails, tails. The number of items in our sample space is 4. The probability of 1 head is the count of how many heads are possible, or how many outcomes in our sample space are possible with 1 head, and divide that by the total number of elements in our sample space. So there are 2 with 1 head out of a total of 4, which makes it a probability of 1 head occurring of being a half, which, if we have a look at our chart up here, gives us an even chance of getting 1 head. Now, if we've got a 3-stage event, in this case we've got 3 coins being tossed, we can get a head, and then if we get a head, it's possible to get a head or a tail on the second coin. And if we get a head and a head on the second coin, it's possible to get a head and tail on a third coin, giving us this sample space here, where we get head, 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 tail, head, so on and so forth. If we take this and put them in a list, it would look like that. There are 8 different possible outcomes from 3 coin tosses, and from that we can count how many of them have more than 1 head. So there's 1 there, there's 1 there, there's 1 there, 1, 2, 3, 4 out of our 8 options, which gives us a probability of a half. Now, if we're not dealing with what could happen, but what has happened, we can use that for prediction. The probability of an event occurring is the count of the times that the event has occurred in the past divided by the number of trials that we had. So in this case, we go around the room and look at the frequencies of eye colors in a group of people. And out of the 8 people that we had in our little experiment, 2 of them had blue eyes, 5 had brown eyes, 1 had green eyes, 8 total. We would take the number of people who had blue eyes divided by the number of trials if we're looking for the probability of blue eyes. In this case, 2 of them out of our 8, which would mean we would expect in the future 1 out of 4 people to have blue eyes. Now the problem, or not the problem, but something to note about experimental probability is that the accuracy increases with the number of trials. So if we have relatively few trials like we do here, it's not a particularly good predictor of what's going to happen on our next experiment. If we'd had 1,000 people and we were trying a similar group of 1,000 people, we would expect the probabilities to be similar. And that wraps up our little review. Thank you, everyone.